Hello everyone. In this unit we are going to be looking into functions, which are one of the constructs that are available in the C programming language to help us organize and structure our code in such a way that it becomes easier for us to manage large code bases. So we have already looked at the core idea of structured programming and how by putting restrictions on the type of control flow that are permitted, in particular going for specific types of branching or for iteration, and by having sequences of statements in the remaining parts of the code, it is possible to impose a certain structure on your program and thereby make it easier to understand. We also looked at the idea of scope, that is in the context of a C program, where we basically look at how variables can be seen by different parts of a program. And now we are going to pay more attention to this part in the middle, which is basically the definition of functions, right? And in particular, we will first try to understand what is the use of functions, where do we need them, and from there go on to how do we declare them, how do we define them, how do we use them in the C programming language. So what are functions? Let's sort of start by looking at some of the background and motivate why we need functions. The first thing is, this is a picture that we have already seen in a different context, which is the output of a compiler, right? So this is basically the disassembled output of a given program. If you look carefully, you will notice that there are many parts over here. For example, this int main essentially corresponds to a piece of C code. These statements here, the int I, int sum equal to 0, are all statements in the original C program. The for loop is also present out here. Each of these, in other words, is interspersed, but those parts of the listing that we have over here don't actually correspond to code. What does correspond to code is these numbers that you see on the left hand side are addresses or relative addresses, meaning that the 0 is the very first address of the program, the address of the very first instruction in the program. 4 is the address of the next instruction, 8 is the address of the next instruction, and so on. Now, as mentioned earlier, this disassembly is based on the RISC-V instruction set. If you try doing it on your laptop or some other machine that you are using, it's quite likely that if you actually used a disassembler there, you might see different instructions, because that would be the x86 instruction set, or possibly ARM if you were doing it on the phone. But the point is, it doesn't really matter. I have chosen RISC-V over here because it's an easy to understand and explain instruction set. What matters to us is there are all these relative offsets followed by colons, which are just a number followed by a colon, which is basically, if you look at it, they are all multiples of 4, right? 0, and then the next one is 4 and 8. C corresponds to 12 in decimal, 10 corresponds to 16 in decimal, and so on. So why is that? Because each instruction, as you can see over here, is actually a 4-byte or a 32-bit value, and that's fixed for the RISC-V 32-bit instruction set, right? That's one of the things that actually makes it simple to understand. Now, we don't really care about the exact numbers over here, right? That's something that it's pretty much impossible for a human being to remember, but the computer is able to interpret these codes that we have. In particular, this code, this FE010113, corresponds to the assembly language mnemonic. Why we call it a mnemonic is, it's because it's something that makes it easy for humans to remember, but this part out here is not something that the computer ever actually works with. It works only with the codes. This part on the right is something for humans to read and understand. So that code corresponds to the instruction add immediate x2 minus 32, which basically says take the register which we call x2, it's one of the 16 registers or 32 registers present inside the processor, and add minus 32 to it and store the result back in x2 itself. Okay. So in the same way, each of these instructions has a certain meaning. When we look at this code, it looks very different from the original C code that started off, which basically was a for loop which added some numbers together, and that was pretty much it, right? It just eventually it returned the sum that it generated out there. So the C code, in other words, looked very neat and simple, but translated into this bunch of opcodes and assembly language mnemonics that are not very easy to understand. In other words, the output that has been generated by the assembly out here is not really a good example of a structured program. But it does not matter, it has exactly the same meaning as the original C program that started out. And what that tells us is the structured program is more meant for the humans who are writing the code rather than for the computer. In particular, you can see over here that you have a continuous block of instructions in memory. It is really difficult to follow any kind of structure over here, and if you were just given a bunch of assembly language instructions, or even worse, just the machine code out here, it would be nearly impossible to reuse any of that. You wouldn't know where to look for what kind of functionality you expect in different parts, right. So clearly this disassembled output is something that is not really meant for humans to spend much time on, whereas it is what the computer actually works with, right. The opcodes are what finally tell the processor what to do. So structured programming, the main premise over there was that by restricting the subset of allowed programming constructs, right, that is to say we do not have just arbitrary jump statements or arbitrary load and store statements, we have a systematic way by which a jump would either be an if or a while or a for, some kind of restricted set of possible statements. A load or a store would have to be either a variable access or a memory access explicitly using an array, right. And an arithmetic operation would have to be written in terms of arithmetic constructs, right. Here what we can see is that there are add instructions, there are store word and load word instructions which are for memory, and there are jump instructions or branch instructions that are for control flow, to basically move around to different parts of the program. They are all interspersed together. Structured programming says you do not just mix them all together any which way you like, you write your code in such a way that the meaning of the code is clear and obvious, and the compiler will then take care of converting that into the opcodes that the machine needs to use. One of the main things that we get as a result is this concept of reusability. We find that certain parts of the code can now be reused by us for different purposes. And what we would like to answer now is, how do we implement these ideas in the C programming language? So the core ideas that we want to sort of achieve over here are, one of them can be called modularity, which basically says that we would like to structure our code in the form of self-contained modules. Each module has the ability to perform certain specific kinds of work, right. So what exactly are modules? Well, I am sort of jumping ahead over here, but you can think of a module as a collection of functions, right. In reality it is more a collection of data as well as functions, all of which are sort of built around the same idea, right, and help us to solve a given problem. So that is one way to think of a module. The C language by itself does not really have a concept of modules, unlike let us say a language like Python. What we do have instead is header files that allow us to call functions that are written in other places, but the idea of modularity is something that is more general than actually implementing it using a keyword called modules, for example, right. Now why do we want this modularity? One is just to get structure, right, that is to sort of clean up the way that we look at our code, and the second is reusability. There might be some parts of the code that we actually want to reuse multiple times. And not just reuse, in general, when it becomes really useful is when we can generalize, that is to say we can actually feed in arguments into the code that we have got, and depending on the argument or the parameter that we feed in there, the result might change, right. All of this is sometimes nicely captured using this slogan, don't repeat yourself, or DRY, right. So the DRY principle basically says don't repeat yourself. If you find that there are two parts of your code that look substantially the same, then you are probably better off refactoring, that is to say pull both that code out into a common portion and replace the actual code with calls or jumps to this part of the code that you have written now, okay. Now just like any other piece of good advice, you also have to be careful where you apply it, right, and overuse of the DRY principle can also potentially lead to problems, but that usually is something that you should pay attention to. But the first thing that you need to think about is, okay, how do you actually recognize that something is a code that could have been, that you could have avoided repeating, okay. So let's look at an example to make this a little bit more concrete. What I've got is a small piece of code out here that essentially has a bunch of print statements, right? So the first printf says sum of the first 5 numbers is %d, and then it basically has a value that's computed out here. And it basically says, so 5 into 5 plus 1 by 2, in other words, I know the formula for the sum of the first n numbers, right, and I'm just applying that. So I'm not actually writing any code to compute the sum of the first 5 numbers, I just use the formula. Now somebody else asks for the sum of the first 8 numbers, fine, I have another printf that has this value 8 into 8 plus 1 by 2, and so on, right. So I have 5 such things. Now there are a couple of things you can notice over here. One is that there's a lot of code being repeated, right. All those printf statements are sort of mostly the same except for a few characters here and there that differ. And the second important thing, which hopefully some of you have picked up on, is the fact that there is actually a typo out here, right. So I wanted to print the sum of the first 455 numbers, I've got 455 out here, but by the time I got to this place it was only 45, right. Now obviously I intentionally brought in that bug, right, in order to prove a point, which is that if I just copy paste and try editing stuff, there's a good chance that I'll make an error, okay. So what can we do about this, right? I mean, clearly this repeating code doesn't seem like such a great idea. Can we do something to sort of, improve the structure of our code? Now with the idea of improving the structure of our code in mind, let's look at what facilities the C programming language provides us to achieve this aim, right? And what we are going to be looking at is what is the structure of a function in C, how do we go about creating one, and what are the different things that you need to keep in mind, and what support does the language provide you for it. The first thing that we can think about is that C provides us the ability to group statements together into blocks, right? And typically what we use is these things which are called the curly brackets, or sometimes the word that is used is braces, right? And curly brackets and braces essentially mean the same thing. It is these symbols, right, which you will see quite a lot of anywhere in a C programming, in a C program. The reason for that is any block of code that is written in C gets encapsulated within these curly brackets, and that essentially converts it into what we call a self-contained block, right. Now we have already seen that there are scoping rules for variables, where if I declare a variable inside a block, then it actually has a different meaning than the variable outside the block, right. What we would like to do is to see how we can go one step further than that. Now in the context of the program that we were looking at earlier, which was basically printing the 5 printf statements that print out the sum of the first 5 numbers, the first 8 numbers, and so on, possibly I might think that maybe that formula 5 into 5 plus 1 by 2, can I extract that out as a separate block of code, okay. So I could think of just taking that part out as a separate block of code. This by itself does not look particularly useful, right. I mean, why would I do something like that? It's not really gaining me anything. The only reason why I might potentially write something like this might be, let's say that I wanted to define some intermediate variable out here and then use it inside this block, and I didn't want that to interfere with other variables that may or may not be defined outside, then a structure like this might actually make sense, okay. Now you are not restricted to only formulas inside a block, you could also have other statements. In fact, a block can have multiple such statements, right. So both of these would be examples of blocks in the C language. But the problem is, as they stand right now, they don't look particularly useful. So let's go one step further and assign a name to the block, right. So that same printf that I have now given it a name, okay. What is the name? It's print underscore sum underscore of underscore 5, which we usually refer to as print sum of 5, okay. And putting underscores between the different parts of the name is a convention, right. An underscore is a valid character in that can be used for naming variables as well as functions. In general, any identifier in C can have an underscore as part of its name, right. So this is a valid name for a function, and the reason why we put underscores is because a space character is not valid in the name of a function. So we cannot have print space sum space of space 5 as a valid function name. We cannot have a hyphen print minus sum minus of minus 5. Now that is actually possible in certain other languages like Lisp and so on, but not in a language like C, right? So to keep it simple, we basically use print underscore sum underscore of underscore 5 and we pronounce it as print sum of 5. Another way of writing it would sometimes be to use what is called camel case, where it might be written with a capital P, capital S, capital O and no underscores, right? So capital P print, capital S sum, capital O F and 5. All of those are conventions. There's no hard and fast rules about how you should name functions, but it sort of makes sense to think of a function as actually performing a computation and give it a name that reflects that. Okay. So what have we done? The same statement, that printf statement that we had, I put it within curly brackets so that it became a block and I gave it a name, void print sum of 5. Okay. This void is a special keyword in C. For the time being you can ignore it. Basically what it says is that this particular block of code does not return a value. It just performs a computation, you call it, it will do something and it's done, right? These brackets over here, which we usually say parenthesis, right? So the round brackets are usually called parenthesis. The parentheses are empty, there is nothing inside them. So it basically says that this block of code does not take any parameters or arguments. Okay. So now what I have done is I have effectively created a block, I have given it a name, and what that means is inside my main function, the main part of my program, I can just refer to print sum of 5, I can then say print sum of 8 and I finally have a return value, because main has also been declared as a block of code, but in this case I have said that main actually returns a value which is of type int. Okay. Once again, that part of it is a convention, don't worry too much about it for now, but all that it means is that main is just another named block of code just like any of these that we have out here. Okay. Now the obvious question would be, why would I do this? I have just sort of increased the amount of code that I have written, because rather than just having this printf directly inside main, I have now put curly brackets, I have given it a name and now I am calling that name out here, right? One possible reason for doing this would be that, of course in this case it's a very trivial example, but if you think about it, if there was some more work being done inside this block of code and I just replace it with a single line over here, when I look at my main routine, my main piece of code, my main block of code, I can pretty much just read the first line out here and I have an idea of what it's going to do. Okay. So in terms of structuring the top level of your code and making it easier to understand, this is still useful. Even though what has happened is I probably wrote more code than I would have written normally. From the point of view of readability and structure and of understanding what is being meant by the code, this actually makes it a bit easier to understand, right? Now in some languages like Pascal for example, a block like this which does not return a value would sometimes be called a procedure rather than a function, right? But in the C programming language we do not differentiate between the two. This is also called a function, right? And something that actually takes a parameter and returns a value is also called a function, right? So we have just sort of simplified and said everything is a function, it may or may not return a value. If it does not return a value, we say that explicitly by putting void out here. If it does not take any parameters, we say that explicitly by putting empty brackets out here or empty parentheses out here. Okay. Now reusability is good, generalizability is even better. What do I mean by generalizability? Why not write one function which I will call just print sum, not print sum of 5, right, which takes an argument or a parameter out here, which I will say is n, which I am also specifying is of type integer, and what that does is it actually prints out the sum of the first n numbers. Okay. So I have replaced the first, instead of saying 5 numbers, I have made that also %d, which will get printed out here, and the second %d corresponds to the formula. So both of these happen properly, and I can just call print sum of 5 and it will perform the computation and print out the value correctly for me. So my main function, in other words, looks very neat. It just has a set of steps saying what I want to do. Exactly how I do it has now been encapsulated into this function out here. Okay. Now there is an additional aspect that we need to keep in mind over here, which is the fact that this particular function has done a little bit more than actually just computing something, right? From the point of view of pure mathematics, we would like to think of a function that just takes some parameters as input, computes something and returns a value to us as an output. Whereas over here this is doing something a bit more than that, it's also printing stuff. Now what's the problem with printing? It's effectively changing the state of the world as we see it at this point. What do I mean by the state of the world? It is essentially the entire environment within which the program is running, right? So I am not actually changing the program, I am not sort of changing any of the other variables or anything, but the program does have what is called a standard input and a standard output. The standard input is how we feed values into the program, the standard output is how we get back values that have been computed by the program. And in this case, by doing a printf, I have changed the state of the standard output. Okay. So this function, as we see over here, is sometimes called a function with a side effect. It has the side effect that the printf has changed the state of the standard output, right? If it was something else that was reading in a value from standard input, that would also be something that changed the state of the overall program. Whereas another function, perhaps if I had just written a function to compute n into n plus 1 by 2 and return that, then interestingly enough that program never changes any other state. It takes n as an input, performs a computation and returns the value. Nothing else is being changed. It has read n but it has not modified anything. It has not written anything to the standard output, it has not read anything from the standard input. Pretty much it is what is called a pure function with no side effects. We will not get into any more detail on pure functions or side effects at this point. The reason I mention it is because in certain programming languages and in certain contexts, especially when you are trying to reason about the correctness of a program, knowing that a function is pure can actually be useful.